Hey, welcome back. This is the last section in differential equations, section 7.5, the Derrick delta function. So what we want to model is a mechanical system that's going along, and then all of a sudden somebody hits it, like with a hammer or something like that, and we want to model that scenario. Okay, so if you look in the book, they have this idea maybe a golf ball being hit by a club. You could think of like a baseball being hit by a bat. Any situation like that. Okay, so we begin with this thing, the unit impulse idea, and we'll define this piecewise function delta sub a of t minus t sub 0, and from that we'll get the Derrick delta function. Okay, so this thing is 0 except in some interval, and in that interval the output will be 1 over 2a. Okay, so 0 from 0 to some point t sub 0 minus a, and then 1 over 2a from t sub 0 minus a to t sub 0 plus a, and then finally 0 again from t sub 0 plus a and on. So to graph that, you locate your t sub 0 wherever that is, and then go over by a minus a, t sub 0 plus a. And so it's 0 everywhere except here, and it jumps up to 1 over 2a, wherever that is. Okay. So what? Well, we can turn this into the Derrick delta function, which is what we want to, and it represents, like, again, getting hit by some external force very quickly by just letting a go to 0. So, in the middle part of this function, if you were to let a go to 0, this thing would go to infinity, and that's kind of what we're after. We also want, so there's like two characteristics that you'll note in the book for what we want in the Derrick delta function. So let me introduce that based off of this idea. So here we want to let a go to 0. Okay, if you do that, you'll get the Derrick delta. Okay, so section 2 then, Derrick delta function is going to be defined just like above. We're obtaining it by letting a go to 0 in this impulse function that we've defined. And in particular, we note first off that infinity issue. So at t sub 0, because that middle part is 1 over 2a, that thing will go to infinity at t sub 0. So first off, delta of t minus t sub 0 will equal infinity at that one point, and then 0 everywhere else. And the other part of this, the way we've kind of characterized it, we want the sort of area underneath this curve to equal 1. So just looking as a rectangle, base is going to be 2a, this distance. If you just take t sub 0 plus a minus t sub 0 minus a, you get a plus a, which is 2a. And then the height from the function is 1 over 2a. So the area is going to be 2a times 1 over 2a, which of course is 1. So we want that to also happen here. So part 2, and you can see it in the book, the integral from 0 to infinity of this guy is equal to 1. Okay, great. The transform of it, then you need to accomplish these problems in the homework. So you'll be adding in this term into like whatever your model is for motion. You know, from the Newton, the sum of the forces on the object is equal to the overall force on the object. So you could just add that term into your differential equation for motion to model the situation. And then you know you'll have to solve these doing transforms. So anyways, the transform we need to get the homework done, section 3, the transform of the Derrick delta function. The Laplace of delta of t minus t sub 0 is going to be e to the negative s t sub 0. Okay, easy enough. It's just, you know, we have so many other transforms to memorize, it's often easy to get them mixed up. The proof of that they accomplish just by rewriting our Dirac delta function in terms of piecewise, the piecewise functions. So delta sub a of t minus t sub 0, you want it to be equal to 1 over 2a. You want to have it 0 and then it turns on to 1 over 2a at t sub 0 minus a. So you'd have 1 over 2a times u of t minus t sub 0 minus a, and then you want it to turn off at t sub 0 plus a. So you just subtract 1 over 2a u of t minus t sub 0 plus a. Then you know how to take transforms of the piecewise functions, and you can see that's what they did here. In this step, they're not using the definition, right? They're not going back to the integral and plugging in stuff, and they didn't like skip steps or something. They just literally took the transform of that and got this expression, and then taking the limit as a goes to 0, we get our transform. Okay, e to the negative s t sub 0, and if t sub 0 is 0, the Laplace transform of that is 1. Okay, so it's pretty simple. This section is that's all there is, and the rest is just kind of doing homework problems. It's just, you know, everything's being thrown at you at once, so it can be a bit overwhelming. Let's take a look at maybe 2 of these. So let's try there's only 7 in the homework, so let's try number 3. Let's see how that goes. We have y double prime plus y equals delta of t minus 1/2 pi plus delta of t minus 3/2 pi. And then we have y of 0 is 0, and then y prime of 0 is 0. Okay. So Laplace transform of this thing, of course, you get s squared Laplace transform of y minus s times y of 0, which is 0, minus y prime of 0, which is 0, plus the Laplace transform of y equals, then the Laplace transform of these things, it's just e to the negative whatever this is, right? So it'd be pi over 2s. You got to tack on the s as well, plus e to the negative 3/2, 3 pi over 2, let's say negative 3 pi over 2s. Okay, clean it up a bit. So this is 0, this is 0. You get s squared plus 1 after you factor out the Laplace transform. Okay, and over here e to negative pi over 2s plus e to negative 3 pi over 2s. Divide by the s squared plus 1. Pi over 2s over s squared plus 1 plus e to negative 3 pi over 2s over s squared plus 1. And then you have some, I guess, these will be those piecewise functions. So automatically you can write u of t minus pi over 2, and then without the e to the negative pi over 2s, that's going to be 1 over s squared plus 1, which is a sine function, but you have to shift it as well. So it would be sine of t minus pi over 2, and then plus u of t minus 3 pi over 2 times sine of t times 3 pi over 2 minus 3 pi over 2. You could simplify these expressions then. So from the the same sine formula, it will be sine of t times cosine of pi over 2, which is 0. And then same sign minus sine of pi over 2 times cosine of t. So sine of pi over 2 is 1, so this will end up being, the whole thing will end up being negative cosine t. And then this guy, sine of t times cosine of 3 pi over 2, that'll be 0 again. Then minus sine of 3 pi over 2 times cosine of t. Sine of 3 pi over 2 is negative 1, so this time this will be just cosine of t. And then you could write up your answer. So y will equal, and I sort of already did the transform there, so I can erase this. I already did the inverse transform. So anyways, y will equal, let's write it, negative cosine t u of t minus pi over 2 plus cosine of t u of t minus 3 pi over 2. Okay, so that should be the answer. Yeah, okay. Let's try a little bit harder of a version of that, right? So they're going to get harder and harder as we go through. Let's try number 6. When I did number 6, I made the silliest mistake, and I didn't catch it. Oh my gosh, I was going nuts this morning. But hopefully you won't make the same mistakes as I do. If you ever get stuck on one, you're just like, I don't know what I did wrong, I'm having a bad day and I'm going to flip out, just send me an email. I can always tell you what the answer is, or you can send me your work and I could look for, try to figure out what you did wrong. Don't always like being the error checker. It's not what I imagine myself doing in life, but it could be a lot worse jobs, believe me. Anyways, y of 0 is 1. And then y prime. I mean, being a teacher is an awesome job, so I don't know. I'm not going to say I don't like it, but sometimes just, why am I doing this? The meaning of life, I guess, is kind of what I get stuck on. The existential questions. Most people don't worry about that, I guess. But anyways, whoops, and I still didn't write down what y of 0 was. I think they're both 0, right? Y of 0 is 0. No, they're not. That would be a mistake. So y of 0 is 1. Okay, so let's make sure I got it right. Y of 0 is 1. Y prime of 0 is 0. Yeah, very important to copy it correctly. I think we're good to go. Okay, so the first guy, s, the Laplace of a derivative, s squared Laplace y minus s times y of 0, which is 1, minus y prime of 0, which is 0, plus 8 times Laplace, s Laplace of y minus 1, and then plus 41 Laplace of y. The mistake I made was right here. I didn't put those guys both in parentheses, so I ended up not distributing the 8. And I just could not figure out for the life of me what I had done wrong. But anyways, that was it. On the other side, then, you have e to the negative pi s, and then plus e to the negative 7 pi s. Okay. Doing a bit of factoring, then we'll have s squared plus 8s plus 41 times Laplace of y. Okay. And then there's these other things. This guy is 0, but there's still a minus s. So I'm going to put that on the other side as plus s. And then there's this character here, minus 8. So I'll put this on the other side as plus 8. Okay. And then, of course, you have e to negative pi s plus e to the negative 7 pi s. I'm going to have to then divide both sides by this quadratic. And this quadratic I'm going to rewrite, okay? Because right now it's not factorable, but if you do like a complete the square, it's going to be an s shift, okay? So anyways, s squared plus 8s plus 8 over 2 is 4. 4 squared is 16. Immediately minus 16 and then plus 41. So that's going to be s plus 4 squared and then plus 25. Okay. All right, so I divide everything by that. I get Laplace y of course, s plus 8 all over s plus 4 squared plus 25, and then plus these two things will kind of have the same result, just one will have a piecewise u minus u of t minus pi, the other one will be u of t minus 7 pi, right? So let's put these guys together and multiply them by 1 all over s plus 4 squared plus 25. All right, so the first character, the first term here is kind of shifted, but it's not shifted correctly because they have an s plus 8 in the numerator, so I need to shift that up, just manipulate that a little bit so the shift is s plus 4. So I'll rewrite it as s plus 4 all over s plus 4 squared plus 25, and then plus the leftover 4. So the first part will be a cosine, and then the second term here will be a sine. Squared plus 25, and then everything else. And of course this part over here will be a sine, and you're going to have to multiply in an additional factor of 1/5 to get the inverse to kind of pan out. 1/5 on this term and the last term there. Okay. So anyways, the first term is good and set up for a shift of -4. And then you have cosine, this first one's a cosine of 5t, and then plus, this is where you have to get a factor of 5 over 5 and then factor out 1/5 and do the Laplace transform. Of course you're factoring out the 4 as well, but then you do the Laplace transform of 5 all over s plus 4 squared plus 25, and of course that would be your sine 5t, right? So you'd have e to the -4t for the shift and then sine 5t, and then the rest of this business. So these guys will give you a piecewise function, so you get u of t minus pi, and then you'll have the Laplace of this thing, so there'll be an e to the -4 times t, but we have this piecewise thing that we have to worry about, so it'd be a t minus pi, and then sine of, and of course I need an additional 1/5 factor to make it work out, and then you have sine of what do we have, 5 times t minus pi, right? And then it'll be exactly the same thing for the other guy, except you have a different shift. So u of t minus 7 pi, e to -4 times t minus 7 pi, and then sine of 5 times t minus 7 pi. The only thing left to do, of course, is if you want to do some additional sort of, identity work to get these to look pretty. This one, of course, sine 5t cosine of 5 pi, right? So that would be a negative sine 5t if you wish. And likewise for this one, that was just a negative sine 5t. Okay. Hopefully then it's all right. And I know, so sometimes it could be quite annoying, but I think I nailed it. Whoops, I lost. Well, once you do the substitution, you'll get a negative out there in front of the 1/5, and then it's ut minus pi sine of 5t e to the -4. Yeah, looks like I got it. Sine of 5t So the only difference is I have actually done that replacement with the negative sine 5t. Pretty simple though, not a big deal, but a really interesting way to produce this impulse function. I think when I was like in grad school, I studied like distribution theory, and they have other methods for getting these impulse functions where they kind of just smush a hill into a really small space, and it mirrors an impulse, but it's a bit more continuous. This is like almost a discrete version, I guess. I don't know. Maybe they're both the same. It's been 20 years, so I don't know. Okay, so anyways, that'll do it for me. As usual, thank you for watching, and I'll see you next time.